The concept of developing hot, dry rock geothermal reservoirs and enhanced geothermal systems stretches back to the 1970s, but only now, after decades of effort across many countries, is the potential for this vast energy resource beginning to be realized. At the center of current efforts lies the Utah Forge Field Laboratory, a DOE-sponsored R&D facility that is managed by the University of Utah, where achievements in drilling, stimulation, and injection production are validating the promise of EGS resources. In early September 2024, a 28-day circulation test was completed at Utah Forge, during which 15 megawatts thermal power was continuously produced, fulfilling a major milestone. The photo shows the steam discharge from the silencer and the production wellhead 16B7832. My name is Stuart Simmons, and I'm one of the geoscientists on the Utah Forge team. This webinar covers some of the geoscientific attributes which control the size and extent of the geothermal resources around Utah Forge. It includes a comparison of differences and similarities between conventional and EGS reservoirs, a simple method for energy resource assessment based on the Utah Forge reservoir, and a conceptual understanding of the geothermal system that is responsible for the resources occurring in the Milford Valley. Before getting into the details, I will start with a short review of the EGS concept and the geological setting of the Utah Forge site. The EGS hot dry rock concept was developed by scientists and engineers working at Los Alamos National Lab with the aim of replicating the benefits of conventional geothermal resources associated with hydrothermal activity. The idea was that geothermal energy could be produced from hot, impermeable rocks by fracture stimulation and cold water injection. While the resource in the form of a large volume of hot, dry rock is natural, the reservoir is engineered, comprising a network of open fractures through which injected water can flow. In creating the reservoir, development of a large fracture surface area is key to maximizing heat transfer. A simple well configuration is shown for Utah Forge, which is fine for testing and research, but in a commercial operation, multiple injectors and producers are required. Hot dry rock potentially suitable for reservoir development occurs worldwide between 4 and 10 kilometers depth in the continental crust, whereas suitable environments at shallower depths relate to anomalous conductive heat flow controlled by geological processes such as magmatic intrusion, and this is the case for Utah Forge. To illustrate the last point, the temperature-depth relationships that distinguish conventional and EGS resources are shown here. Conventional resources occur in hydrothermal environments, and they are closely associated with near-boiling water temperatures, which results from convective heat transfer and fluid flow through permeable rock. By contrast, EGS reservoirs occur at deeper levels where thermal conditions are governed by conductive heat transfer in solid, impermeable rock. The average crustal gradient of 25 degrees Celsius per kilometer is shown in comparison to an anomalous conductive thermal gradient of 50 degrees C per kilometer, and such differences in temperature gradient controls the depth and grade at which EGS resources can be developed. Now turning to the location and the geological context, Utah Forge is situated on the east side of the Milford Valley in southwest Utah. It lies on the eastern side of the Basin and Range province, as shown on the right, close to a cluster of conventional geothermal fields that includes Roosevelt Hot Springs, Cofort, and Thermo, shown in the close-up view on the left. Additional fine-scale features include the locations of known volcanic centers and widely distributed hot springs. The Utah Forge site was selected by DOE via a competition over a 3-year period from 2015 to 2017, during which reservoir characteristics were documented. But this was not a virgin site, and much useful supporting information was available from earlier DOE-sponsored research in the area going back to the late 1970s. This activity led to the commissioning of the Blundell Power Station at Roosevelt Hot Springs in 1984. Not only was this the first geothermal power development in the basin and range, it also proved to be one of the hottest, having a resource temperature greater than 260 degrees Celsius. Fast forwarding to the current situation, the Utah Forge site lies 4 kilometers west of Roosevelt Hot Springs, shown in the 3D block model. The stimulated reservoir is localized around 2 deep deviated wells which represent an injection production well doublet. From a wide range of surface and subsurface measurements, the following characteristics have been determined. The reservoir lies between 175 and 225 degrees Celsius at 2 to 3 kilometers depth. It is made of very tight crystalline rock called granitoid. It occurs in a region of high conductive heat flow. It is endowed with a densely spaced multidirectional fracture network. It exists in a zone of low to moderate natural seismicity. It lacks native pore water, and it has a magmatic heat source. This aerial perspective provides an expansive view of the Milford Valley looking northwest across the Utah Forge site. The wells 16A and 16B are in the upper left corner, with deviated legs that extend 4,000 feet to the lower right corner near the 78B well pad. All the other wells have vertical trajectories, and they are used for seismic monitoring. Turning to the geological attributes, the map and cross-section show the 2 main packages of rock types occurring in the Utah Forge vicinity. Layered sedimentary rocks make up the basin fill strata, which are represented by yellow to pink colors. The upper part of this sequence is made of detritus eroded off the mineral mountains to form the alluvial fan deposits on which the Utah Forge site is located. Geothermal resources are entirely hosted in granitoid, pluton, and gneissic rocks, which are the same rocks exposed in the core of the mineral mountains to the east and shown in the green colors. The most recent evidence of magmatism on the surface is related to the 0.9 to 0.5 million-year-old rhyolite centers representing eruption of about 3 cubic kilometers, shown in the magenta colors. These are relatively small erupted volumes, and the timing of emplacement is rather ancient in comparison to what might be expected of an active magmatic center. Lastly, the cross-section shows the thermal structure in which the shapes of the isotherms distinguish convective heat transfer associated with hydrothermal activity at Roosevelt Hot Springs from conductive heat transfer occurring beneath Utah Forge. The boundary between these 2 distinct heat transfer regimes coincides with the position of the Opal Mountain Fault. The stimulated volume enclosed by the black box represents the EGS reservoir that is centered on the deviated legs of the injection and production wells labeled 16A and 16B. These wells have a shallow angle rather than being horizontal to enable placement of tools and equipment required to undertake field experiments in the reservoir. Note the production leg in red overlies the injection leg in blue, and the 2 are separated by about 300 feet. The temperature logs from all the wells indicate an anomalously high conductive thermal gradient of approximately 70 degrees Celsius per kilometer. The reservoir rocks are well characterized and made of plutonic rocks, granite to diorite in composition, and collectively they're referred to as granitoid. They're also high-grade metamorphic rocks made of gneiss. These rocks contain a very similar mineralogy made of aluminosilicates, including feldspars, micas, and amphiboles, plus quartz. We are fortunate, too, that the core of the mineral mountains exposes the same rock units as those hosting both geothermal resources at Utah Forge and Roosevelt Hot Springs. One benefit is the ability to better appreciate the interrelationships between the different rock types. More important, though, is the evidence for widespread extensive fracturing, which is believed to facilitate EGS reservoir development. Through geophysical logging of wells at Utah Forge, analogous sets of fractures were identified, and the fractures having roughly north-south orientations are the ones that are prone to dilation during stimulation. Although there is no modern volcanic edifice, hydrothermal activity and the ancient eruption of rhyolite volcanic rocks are the indications of a long-lived magmatic center. Apart from the localized occurrences of steaming ground at Roosevelt Hot Springs, evidence of anomalous heat flow are largely concealed beneath the surface and determined mainly from temperature gradients measured in shallow and deep wells dating back to the 1970s. For example, the 200 degrees Celsius isotherm at 3 kilometers depth encircles both Roosevelt Hot Springs and the Utah Forge site, and this covers an area of at least 80 kilometers square. The true extent of the geothermal system, however, appears to be much larger. One line of evidence is the outline of mantle helium occurrences detected across the central to east side of the Milford Valley, shown in magenta. Most of these occurrences are based on analysis of cold groundwaters obtained from shallow wells, but they also include hot production fluids from Roosevelt Hot Springs. Their extent covers 270 kilometers square and provides an independent guide to the possible limits of the geothermal system. In support of this interpretation, the geothermal company Fervo recently completed a vertical well to 15,750 feet depth near groundwater well labeled NSW and reported a maximum temperature of 520 degrees Fahrenheit, equivalent to 270 degrees Celsius. Fervo is now in the process of building a 100 megawatt power plant directly adjacent and west of the Utah Forge site, for commissioning in 2026. And validation of a large resource area will boost confidence in developing and expand power production into the future. Information about the deep roots of the geothermal system are drawn from the west to east cross-section of the resistivity structure based on a magnetotelluric survey shown on the right. The top image is the geological interpretation of the geophysical model on the bottom. In the latter, dark red-brown to dark blue represent electrically resistive solid material that correlates with low porosity and low permeability granitoid, whereas the warmer colors, yellow to red, represent conductive material containing a proportion of fluid in the form of water or melt. The location of the crust-mantle boundary is approximated by the dashed white line. In the geological interpretation on top, the main elements include the extent of the basin fill strata and of the underlying poorly permeable basement rock in green. At deep level, the magmatic regime involves underplating of deep mafic melt that induces widespread partial melting of the lower crust, indicated by pink crosses. And estimates based on heat flow suggest that recently solidified partial melt exceeds 400 cubic kilometers. The fluid flow path related to hydrothermal activity at Roosevelt Hot Springs is shown by the upward pointing arrow that bisects the shallow crust. The surrounding yellow box outlines the zone of convective heat transfer. By contrast, to the west lies the region of conductive heat transfer that hosts the Utah Forge Reservoir. The subhorizontal red lines represent its characteristic conductive thermal gradient. The previous two slides provide a sense of the huge size of the geothermal system, which is largely concealed but responsible for transferring heat through the crust. We now turn to examining details of the known hottest parts of the system at less than 3 kilometers depth, where convective and conductive heat flow regimes occupied either side of the Opal Mound Fault. The conductive region to the west has a deep heat flow of 0.1 to 0.2 watts per meter squared. That corresponds to the linear temperature gradient of 70 degrees Celsius per kilometer measured in the deep wells beneath Utah Forge, and that are characteristic of the hot dry rock reservoir. In terms of the overall EGS resource, the Utah Forge Reservoir sits on the shoulder of the anomaly as the contours slope off downwards to the northwest. The convective region to the east of the Opal Mound Fault has higher and concentrated heat flow of 3 to 7 watts per meter squared. The main zone of hydrothermal upflow covers a region of about 1 kilometer square where the geothermal production field is located. The reservoir temperature pressure regime is represented by hot hydrostatic boiling point for depth conditions to 700 meters depth, below which it goes vertical to a pre-production temperature of 265 degrees Celsius. A graph showing the comparison of the two regimes on a temperature depth diagram follows. Remembering that the orange field represents the temperature depth characteristics of conventional resources in contrast to those of EGS resources in yellow, the positions of Roosevelt Hot Springs versus Utah Forge are plotted to emphasize the key difference between convective and conductive heat transfer regimes. In convective regimes, heat flow and fluid flow are concentrated together, creating comparatively high-grade resources. In conductive regimes, heat flow is more widely dispersed by solid-state conduction, creating lower-grade resources that occupy vast volumes of rock. With the foregoing, we now have a basis for summarizing other main differences between conventional and EGS resources. As has been emphasized, they are distinguished by the mechanisms of heat transfer, and these dictate where and how reservoirs are tapped. Conventional resources occupy convective hydrothermal environments having high power density in high permeability rocks. For commercial reasons, they are generally drilled to a maximum of 3 kilometers depth. Production fields support tens to hundreds of megawatts of generation, but their occurrences and size potential are localized by the geological controls on rock permeability and the deep-seated supply of heat. EGS resources occupy conductive hot dry rock environments having lower power density in low permeability rocks at deeper levels in the crust. However, the resource potential is vast, with the possibility of producing thousands of megawatts of electricity. Environmentally, a key concern is the risk of induced seismicity as occurred in Basel, Switzerland, and Pohang, South Korea. Such risks so far have been minimized in the Milford Valley, in large part due to the state-of-the-art seismic network and use of a traffic light system to manage operations and mitigate the triggering of large events. This is very much an important aspect of EGS development that continues to be the subject of ongoing research. In the last part of this presentation, I want to touch on how the potential productivity of an EGS geothermal resource can be estimated using Utah Forge as an example. In hot, dry rocks, it has long been known that a confident upper limit of available thermal energy, designated Q, can be determined from a simple stored heat calculation shown on the right. The main variables to consider are the rock volume, the rock porosity, which is effectively zero, rock density, and the specific heat of the rock. Also factored into the formula is the temperature difference between the reservoir temperature and the cutoff temperature designated T0. In EGS, energy production, heat is extracted via cold water injection from a hot dry rock reservoir. The result is cooling of the reservoir over time, and the cutoff temperature represents the coolest temperature to which energy and power might be produced. In the calculations that follow, the reservoir temperature is taken to be 210 degrees Celsius and the cutoff is 120 degrees Celsius, so that the delta T is 90 degrees C. For simplicity, the reservoir volume is defined as a cylinder that circumscribes the length of the deviated legs in wells 16A and 16B, as shown in the diagram on the left. The cylinder radius of 500 meters is based on the extent of induced microseismicity detected during reservoir stimulation. With these values, the reservoir volume turns out to be about 1 cubic kilometer. Shifting to the temperature versus depth diagram on the right, the Utah Forge temperature gradient and the cutoff temperature limit the delta T of the calculation, and the pink filled region in between represents the temperature range of producible energy. The resulting available thermal energy is 2.4 times 10 to the 14th kilojoules. If we then consider a reasonable recovery factor of 20% and consider continuous energy production over a 25-year period, the thermal power output of 62 megawatts is calculated. Converting that value to electrical power output, which entails multiplying by a conversion efficiency value of 10%, gives 6.2 megawatts. Such a calculation highlights three parameters of resource assessment. First is the stimulated volume of rock from which heat can be extracted, which is reasonably well constrained. Second is the proportion of heat that can be recovered, called the recovery factor. In the calculation, a value of 20% was used based on prior experience in other projects worldwide, and it represents the largest source of uncertainty in resource assessments. Third is the conversion efficiency of thermal to electrical power, which based on published reports is about 10%, but improvements in technology suggest it could increase to 15%. As the Utah Forge footprint is only about 2 kilometers squared, the main source of additional geothermal resource is in hotter, deeper rocks that underlie the existing reservoir. The graphic on the left shows such development through drilling and stimulation of 2 additional and deeper reservoir volumes down to a depth of 5 kilometers. Taking the same input values as in the previous calculations with adjustments to account for the hotter reservoir temperatures, the available energy increases to 1.3 times 10 to the 15th kilojoules, which for a 25-year period represents 267 megawatts thermal or 26.7 megawatts electrical. Clearly, development to hotter, deeper conditions significantly increases by a factor of 5 the total producible energy. Now let's examine the results of the circulation experiment and the energy produced over 28 days in August-September 2024. During this trial, cold water was injected into 16A and hot water was produced from 16B at 185 degrees to 196 degrees Celsius at a flow rate of 10 barrels per minute. The resulting power output was about 15 megawatts thermal. This value is smaller than that shown a couple of slides previous, but we also know from other lines of evidence during the test that reservoir fluid flow was restricted to stimulated fractures in the rock volume between the two deviated well legs. Accordingly, a more realistic estimate of the volume of rock from which heat was extracted is shown in the graphic on the left, in which the reservoir volume is contracted to better represent the zone of fluid flow. The predominant pathways numbered 3, 4, 8, and 9 represent the stimulated fracture zones controlling injected fluid flow through the reservoir as confirmed by tracer testing and downhole spinner measurements. On the right, a revised value of the stimulated volume, now only 100 meters in radius, is shown. The total available thermal energy is 3.4 times 10 to the 12th kilojoules, which is 1 to 2% of that originally estimated. Using the same approach as just presented, but now spreading production over a 5-year period and considering a 50% recovery factor, yields power production of 11 megawatts thermal and 1.1 megawatts electrical. In comparison to the power produced during the circulation trial, the recovery factor of the test exceeded 50%. The foregoing shows that just a fraction of the available heat in proximity to the wells has been produced. Looking at the bigger picture, the orange box represents the 1 kilometer square footprint of the Utah Forge Reservoir. Considering the 40 kilometer square area inscribing the known zone of high-grade conductive heat flow west of the Opal Mound Fault, the total resource between 2 and 5 kilometers depth could exceed 500 to 1,000 megawatts electrical. This assumes a 10 to 20% recovery factor and a 10% conversion of thermal energy to electrical energy, and improvements in both would potentially double to perhaps triple such estimates. In sum, the stored heat calculation provides a simple, first-order method of the potentially available thermal energy within hot dry rock reservoirs, and it lays a foundation for assessing field tests and performance. It does not replace numerical modeling, which is being used to advance fine-scale, spatial temporal understanding of energy extraction and production, but it does motivate all the effort that is being placed on finding cost-effective methods for resource extraction. To wrap up, the key points of this presentation are summarized. First, Utah Forge represents a very small part of a regionally extensive geothermal system that is driven by deep magmatic heat. Second, the conventional hydrothermal resource at Roosevelt Hot Springs east of the Opal Mound Fault, which has been in production since the mid-1980s, is localized and high grade compared to the widespread endowment of EGS energy hosted by hot dry rock. The EGS resource is lower grade, but huge, and steps to tap this resource are just underway. Third, the stored heat calculation provides a simple, quick method of assessing the potential energy of an EGS hot dry rock reservoir. With some conservative assumptions, there's enough thermal energy within the vicinity of Utah Forge between 2 and 5 kilometers depth to provide 500 to 1,000 megawatts of power at a minimum. This is what drives EGS research, particularly in advancing methods and techniques to extract energy effectively and efficiently. Utah Forge would not exist without the long-term sponsorship and commitment from the U.S. Department of Energy. Deep thanks for their ongoing support, assistance, and advice, which lies at the heart of EGS technology advance. Additional support comes from the Utah Trust Lands Administration, Beaver County, the Utah Governor's Office of Energy Development, and Smithfield Foods. And please, if you are interested in more information or news about Utah Forge, please check our website. Thanks for watching.